Thank you very much. So this is the English talk, and so it's great to speak in you in Chebyshev laboratory, especially that the project is supported by Anton Baranov grant. And so the subject is just Bezout equations, which started in 1624, the first publication. Not counting Diaphant, of course, but Diaphant is not at all published. It is in some. So the Bezout equation is here. So the some element of some ring or some algebra f1, fn are given, and you look for solutions gk which satisfies this additive equation, and the necessary and sufficient condition is also obvious, at least tautological, but however, so to solve it, it's necessary and sufficient that the data fk do not belong to any non-trivial ideal in a ring. The history, so my talk is in two parts, even in three. So some review of the long history of the equations, then description of my field, of this axiomatic, of the algebra, for which, and then the statement of the theorem and the proof. Okay? So first of all, some abridged history. We started with exactly Claude Gaspard Bachet de Mézières, 1624, who proved the following theorem, that the Bezout equation in the ring of of integers has a solution if and only if fj have no common divisor. Then it was published, however. He was a teacher in the Jesuit college in Milan, Italy, and so he published as some learning material in this college, this theorem with the proof. But it was forgotten, of course, and 150 years later, Bezout proves the same result, and also the result for the polynomials. And this is from Bourbaki treatise, when the term of Bezout equation became known. Not Bachet de Mézières equation, which is more complicated to pronounce, if you know. And Bezout equation is just from Bourbaki as a terminology. So this is this Jesuit, Mézières, Etienne Bezout, is here, who was also a teacher in École Polytechnique. École Polytechnique in the modern state did not exist, but it exists some artillery school where he teaches. Okay, so after we go to, so this is 17th and 18th century, now to 19th century, it's just Alain Hilbert. And in 20th century, there was many people, but in analysis, it's mostly starting with Carlson, where our story continues. And Hilbert gives the modern shape to the theory of Bezout equations, and linked it to algebraic geometry, and proved in particular for polynomials in several variables. It is interesting to say that for algebraic geometry is maybe not this Bezout, this Hilbert theorem, which is of interest, but the description of finally generated ideals. I mean, given a set of polynomials in Cn, in C capital N, so you need to describe this set of this ideal generated by Fn. And nobody tested what in analysis is common, whether it's true or not that a polynomial f belongs to this ideal if and only if this is less than summation fk of z for 2z of Cn. It's after some quiz among the specialists in Bezout equations, I became informed that it's not solved problem. So it's you know that Hilbert described it, but only multiplicity-free polynomials. I mean that if a polynomial is equal to 0 on the common zeros of Fn, so some power of m belongs to this ideal I. This is the principal Hilbert theorem. But whether you can do it without this power, it's not clear. And Carlson, after a question by Kakutani, so from 1941, a long story, to the 1962, answered to this Kakutani conjecture whether in the algebra of bounded holomorphic function on the unit disk or in the half plane, this obviously necessary condition is sufficient. Yes, it is sufficient. But do not forget, if we speak about the history of the subject, do not forget the impact of Donald Newman to this, which is quoted in Carlson paper, but not completely. It is so, in particular, it's Newman who make two principal steps in the Carlson proof. I mean the reduction to free interpolation problem on a sequence of points, and to solve this interpolation problem, so you need to make some estimates of Séguin or Carlson potential there, and to prove so-called Carlson embedding theorem. It was some story about it, and I just will give you 2 minutes to read the following sentence. So let's consider it. The story between Newman and Carlson, exactly this one, by Leon Ehrenpreis, is a friend closer friend of Newman from the school years, and know him very, very well, and the whole stories of this famous theorem. So it is, I mean, it is not a lone story like this with Newman. He gave many ideas to many other mathematicians, in particular exactly about free interpolation, or about many other people. And Leon Ehrenpreis, who himself is a famous mathematician and the author of so-called how it's called, principal theorem in convolution equations in several variables. He finished his essay on Donald Newman in this journal by the sentence that Newman was a Vivaldi of mathematics, because he started to quote Newman, who called Erdős like Mozart of mathematics, and so he classed it in musical terms and go to Vivaldi with Newman. Okay, this is Newman. So I was presented for many his talk. It was very clever. Okay. So now, after Carlson, we come to the Banach algebra setting for Bezout equations, and it changed the name and more or less, and became a part of so-called Corona problem. So the Corona problem is here. You have a commutative Banach algebra with unknown maximal ideal space, and some known part S, some visible or known, which you can identify, and the Corona by definition, is a function of A and S, and is just the complex homomorphism which are not accessible starting from the visible part S. And the corona problem is whether this corona is empty or not. The Gelfand theory reduces immediately the problem to the Bezout equation. And so there is no corona if and only if this necessary condition where Z belongs to this visible part S is also sufficient. And you can immediately see that the problem is in non-symmetry of the algebra, so in some kind of holomorphy, because for symmetric C star algebra in CK and so in infinity there is no corona. And Carlson result after Hilbert was the first one in holomorphic surrounding. Okay, so we need some instruments to see corona, because the spectrum is invisible, so we need to look it. In fact, the search for a corona started not with Carlson, but I can say with Wiener and Pitt, who proved in 1938 that the algebra, the convolution algebra of all measures on the real line has a huge corona. Huge corona means that there exists a measure mu whose Fourier transform is separated from 0. This is a visible spectrum. Visible spectrum is the values of Fourier transform are for the real line or the dual group for arbitrary locally compact abelian group. This is visible, and so it is separated from 0 on the visible spectrum, but there is no measure such that we have this equation. So the order 1 Bezout equation is not solvable, okay? Which is always the case, save for H infinity algebra. And so later on, Hewitt and Trudin proved that the similar facts, so the presence of corona, is true for arbitrary locally compact abelian group, if and only if it is non-discrete. If it is discrete, there is no corona, of course, because this is simply absolutely convergent Fourier series on the dual group, and you have yet another Wiener theorem that there is no corona. And so Carlson, I repeat what we know. For many other open set, there is also known this one, and there is not known any open set omega in the complex plane for which the corona is not empty. This is a good problem. A very interesting, even astonishing result is the Dawson PhD thesis. It seems that after he was not published anything. So an example of subalgebra, uniform. So uniformly closed subalgebra generated by two functions. So by polynomials and by this function, which is in H infinity, which has corona. I will explain even why it has a corona, because it is of interest from general point of view. In fact, even we can consider one generated algebra, just one. But with this is not the disk which is the visible part, and this is. So let's consider this algebra generated by Z and 1 minus Z to the I. What is 1 minus Z to the I? This is e to the I logarithm 1 minus Z minus argument of 1 minus Z. Z is in the unit circle here, and so 1 minus Z is in something like this. And so our function f of Z is between e minus pi over 2 e to the pi over 2, And so the visible part of the maximal ideal space of this algebra is, of course, D. So for every point Z in D, this is the complex homomorphism. And if Z is different from Z prime, so this is a different homomorphism. So the disk D is naturally embedded into the maximal ideal space of this algebra. But there is a huge corona, because even the inverse of this function, 1 over f, does not in algebra. Why it does not in algebra? Why? And this is a good question, because why there exists corona? What are the general reasons what corona comma? And this is just the beginning of the conversation about that. So the answer, there is no answer. My answer, which is not total, but almost, it's cover many known examples, but not all of them. So it is from the hidden holomorphic extension and point evaluation. So you have some domain here where the function defined, but in fact it can be continued holomorphically to some other domain, and there maybe here it may be separated from 0, but here it's maybe it vanished. So if we forget the adjective holomorphic in this extension, this sentence is trivial, because because to having no corona, we need that the closure of D coincide with the all maximal ideal space. So if there is no such point, so there is no corona. But the point is just in holomorphy. So what we can see, I'd like to say that we cannot approximate 1 over f. It does not in the algebra, so we cannot approximate it by this by polynomials in Z and F. So why we cannot? Because take Z on the real interval here, then what and what, and let it tends to 1. What we will have? So yeah, first of all, f is unimodular for the real. The argument is real to 0. So this is 1 over f of z, 1 minus f of z p, like this. And here on this interval it is unimodular, so this is equal to 1. And when z tends to 1, so what make f of z? F of z is in the unit circle, and it turns. It make infinity of around 0. So we can choose some sequence such that f zk tends to w an arbitrary point on the unit circle. And so
why? Sorry. I is fixed.
Huh?
I is fixed. Therefore,
I?
No, not this.
This one.
You have two i's in definition of f. Some power of 1 minus z. In definition f, you have
I.
Not this one.
No. Where?
What?
Yes, it's another. There is no other I, no?
So it is fixed.
Huh?
F of zk, not zi.
Okay. So I will have that 1 over fp f fz, the maximum over the unit disk, is not less than this limit, which is 1 minus w p 1 w. Okay? And P1W, this is just a polynomial in W. Okay? So this is some 1 minus WQW, where W is arbitrary point here. And so the maximum in W, which is equal to 1, so we cannot approximate, and it is not in the algebra. The same effect as okay, so it's very simple and obvious algebra where we have a corona already. Okay, so if we continue in several variables, so we can remember Brian Cole, who constructed the first Riemann surface, such that H infinity omega has the corona. So it is not the Wiener-Pitt phenomenon. So for H infinity over an open set or over the Riemann surface or analytic variety, so the first order Bezout equation is always summable. Okay, so if f is bigger than delta, 1 over f is also in H infinity, no problem. But in Brian Cole, this is the two-order Bezout equation, which is not solvable despite the necessary condition which is satisfied. And then, so Sibony and Sibony-Farnais and some other and many other people constructed quite complicated but pseudo-convex domains in Cn with the corona. But however, for the classical ball and polydisk, the question is open, and there is no example of open set in Cn where there is no corona. No good open set, because in Cn there is this forced holomorphic extension, and so in particular the people analyzed the proof of the Carlson theorem. The proof of the Carlson theorem suggested by Newman, by the Newman scheme, it starts with the induction in n, in the order of the equation. Started with writing equal 1 minus fn, and so on. And so the first question, whether the induction works always. I mean, if you can solve, say, the Bezout equation, all Bezout equations with two terms, you can solve Bezout equation with arbitrary number of terms. And the answer is no. And this is Nazarov who proposed a very clever example, exactly based on forced holomorphic extension in Cn. Not all domains are domains of holomorphy. And he constructed, given a natural number n, he constructed an example of an algebra where all n minus 1 order Bezout equation are solvable, but there is n order Bezout equation which has no solution in this algebra. Okay, so it is about. Now I will comment very quickly the different reasons why the corona appears and what is the nature of this corona, because the examples, however, are different. Even what I listed already. I listed what? The measure algebra, there is no any analyticity. Okay, the Dawson algebra, there is a holomorphic extension. And there are the other. So first the convolution measure algebra. What is the corona? The corona is in Wiener-Pitt phenomenon. As I said, that on the visible part of the spectrum, on the dual group, the Fourier transform is separated from zero, but the function is not invertible. Why? It's a good question. You need to follow the proof. The proof consists in so the only legible proof, because the proof of Wiener-Pitt nobody can interpret. I don't know neither the book or source or a living person who understands what is written in this paper 1938. It is absolutely illegible. As how to say, yellow peril. It's not yellow, but almost. Yet another book by Wiener was called Yellow Peril in these years about stationary processes. So, but the legible proofs start with constructing the measure on a non-discrete abelian group such that the powers, convolution powers, are independent, just with disjoint supports. And because they are independent, so you can consider it as independent variables, so-called Bohr lift. And then the analyticity comes. So you can extend it to the polydisk and find the point where the real Gelfand transform has a 0. And this is the proof. So this is the technical tools. Uniform algebra, what the Cole or the Dawson, or maybe there is other, it use the maximum principle as here, the maximum principle, and the solenoid effect, that something turn round, as I show it here, the value of f of z in this simplest case, and in the Cole case also. So they turn it and have some approximation. H infinity trace algebra, it's different. So not only subalgebra, here is the subalgebras, like in Dawson, but also the trace algebra, H infinity trace over sigma. Sigma is a subset of the unit disk, say, and we consider this Banach algebra with the quotient norm, the minimum of the norm of functions, which is given, which has the given trace. So the result is that there exists sigma for which there is the corona. For instance, if you have, if sigma is on the 0, 1, a sequence which tends to 1 and is not a finite union of geometric progressions. So there is a corona, and for some other sigma there is no corona. Say for sequences which approach to the unit circle with geometric rate. And it is the reason, the corona type, and the technical reason why it appears is quite numerical, it's metrical. You need to consider more or less the Lipschitz constant of H infinity functions with respect to pseudo-hyperbolic metric. And then so playing on this difference, if you consider on the set sigma and on the whole unit disk between this ratio, Lipschitz ratio in pseudo-hyperbolic metric, you can decide whether there is a corona or not. And Fourier multipliers, it is, I don't mention it yet, for multipliers, the question is quite popular. I mean, so especially for point-wise multipliers, in some Dirichlet algebra in one and even in several variables. And So there is no corona, there is no corona, there is no corona. The results are like this. But unexpectedly, when you come to discrete case, not in function algebra in an open set of Rn, but just to Fourier multipliers, I mean on the real line or even on this, so the situation changes. Say, consider the Fourier multipliers on the unit disk. So the sequence is lambda n such that this mapping can be extended up to bilinearity to a bounded mapping on the space LP of mu, where mu is a measure on the unit disk. So the result is that there exists W, a weight which even satisfies the Mackenhaupt condition, so that this is a basis, not a Schauder basis, not unconditional, but such that the multiplier algebra of L2 TW has a huge corona. Huge corona. But there exist many other also, W also satisfying, or even not if you want, because this is not of interest, but also A2 if you want, and even better, whereas there is no corona. So what is the reason? At least in known examples, it is more or less the same. It happens that for this case, lambda n is the values of some symbol on a part of the circle, say alpha n, where alpha is the unimodular. And so this gives the visible part of the spectrum. The visible part of the spectrum, this is the closure of this lambda n. So this is phi of t. If phi is continuous, but if phi is holomorphic, there is a holomorphic extension to the unit disk, and the real spectrum of the corresponding multiplier is equal to phi of d. And so this is, I mean, that the same reason as in the first or other. So some hidden holomorphic extension, and the quite rough reason with the Wiener-Pitt phenomenon in this case. Okay? So the last picture of the introduction, and then I will describe my subject today. So I'd like to recall you that the Bezout equation is not a game. They are important. So not only starting with number theory, with Diophantine additive number theory, and then in algebraic geometry with this problem of finitely generated ideals and the intersections of zeros of the polynomials, but also say for normally solvable partial differential equations with constant coefficients. Because if you have a system of partial differential equations with polynomials, this system is normally solvable in Hausdorff sense if and only if the corresponding in the dual space, in the dual algebra, finitely generated ideal by this polynomial is closed. And this is closed, so we are the same problem to describe the finitely generated ideal of this type. And so in complex analysis, this is also the problem of finitely generated ideals, and the corona problem, and what is maybe the most important of all 5 points here, this is independently discovered with Carlson, I mean in the beginning of 60s, that the corona, the Bezout equation is just adequate language for the control, for the feedback stabilization of linear controllable systems. Because so here the transfer function f is usually the ratio of 2 rational functions, matrix valued maybe, and so the possibility to construct this feedback which stabilizes the system, I mean which leave it bounded in when time goes to infinity, is necessary and sufficient that the Bezout equation this is solvable. This is and so this is so they need of course the algorithm to find the solutions, and they need first of all the estimate of the solution. And say I also recall that say for the proof of Carlson the estimate is also primary, because you start with very smooth data and smooth solutions, and then pass to the limit, having some good estimates of these solutions. So now is my subject here. Okay. So the idea, in fact, the message is very trivial, simple. So it is one sentence, the following. So in the Carlson proof is quite complicated and contain in particular non-transparent duality and embedding arguments. And so my message is that if we work in the algebra, in holomorphic algebra, which are the holomorphic part of algebra of functions, where the risk projection is bounded, so the proof is elementary, very short, and always positive, and give a very good estimate. Okay, this is what I'd like to explain. So in particular, so this is some abstract axiomatic scheme, which applied in particular to Lipschitz spaces, so with some number of derivatives which satisfy Lipschitz condition, which is an algebra, or the Berling-Sobolev algebra, say, think about Wj which is equal to the power of j. The Sobolev spaces correspond to p equal to 2, and Wj is equal to some power of j, some positive power of j, or the Dirichlet-Wiener like this, or okay. So in my setting, there is no problem in corona, because all these algebras are algebras of smooth function on the unit circle or in the closed unit disk, but the problem is in the estimate. So I recall that in applications and even in the proof of many less trivial theorem, the estimates are the principal point. Okay. So how to measure? Because if it concerns the estimate, so we need to fix some notation and some tools. So considering the data, so we will use the L2 norms in the direct product of the algebra A n times. Then we consider the list, a list because it's numerous. It's maybe empty. It's possible that this is empty, so the infimum is equal to infinity, of course. Yeah, but if they exist, they are several, and but we consider here is not a solution, but this is the minimal value of the norm in this sense. of the solutions of this equation. Okay, and then so we consider the worst case. So we consider the normalized data in this sense, which are separated from 0 by a number delta. The modulus of f of z, this is the length of the corresponding also Euclidean, of course, fk of z square 1/2, this is f of z. Okay, so separated by delta, and so for n equal to 1, when the order of Bezout equation is equal to 1, this is simply the best possible estimate for inverses in the worst case. Okay, and I'd like to recall that, or just repeat that normalization is necessary. Without normalization, the problem is empty. All these things are always equal to infinity, and there is no problem to compute. So now the description of the class of algebras. So I will consider first the symmetric algebras on the unit circle. So continuously embedded in L infinity and symmetric with respect to this convolution and this one also. Okay, and keeping the norm. It is not so important, but to compute some constants, I will suppose that this condition means that the unit circle is the natural domain of the definition, that this is a spectral radius of the generator. The most principal, the most important, this one, that the risk projection is bounded on our algebra. And this is technical also. I can replace it by simply the Poisson mean is bounded. For instance, if f is rotation invariant, like Lipschitz, Berling-Sobolev, and so on, all algebras I listed are rotation invariant. So this is automatic, and this is not, of course. So start with the remark that in the symmetric algebra there is no problem estimating Cn in terms of C1. Because just by this obvious solution, if you have the data which is separated from 0, 1 over f and modulus of f square is in the algebra because of symmetry of this algebra, and multiplying by fj bar, we get the solution with the obvious estimate like this, but delta square, however. What is not so pleasant, as we can see. Okay, and the second part is the principal object. So because we are interested in holomorphic functions, so A is a symmetrizable holomorphic Banach algebra in the unit disk if there exists a symmetric algebra on the circle, like before, such that A is the holomorphic part of F. So I can say that it's symmetrizable if you can complete it up to symmetric Banach algebra on the unit disk. And this is technical condition that it is sequentially weakly complete in this sense as described. So the examples are Lipschitz, Berling-Sobolev, which I just will give a little bit more detail. So what is Berling-Sobolev? So I can say that it's the Fourier transform of discrete LP, weighted discrete LP. Symmetric if the weight is symmetric. It is an algebra if Wn is more or less regular, say logarithm Wn is concave, and this supremum is finite. There is no less than plus infinity. I'm sorry. Say for Sobolev power like Wn, as I said, this condition, this is finite, is equivalent to say that alpha is bigger than 1 over p prime. From the general point of view, I can recall you that this is an algebra, Banach algebra, if and only if it is embedded in C. on the unit circle. And because it is z to the n is unconditional basis here, so if and only if it is embedded in Wiener algebra, okay? And so also two more different symmetrizable algebras, but H infinity is not. Not because of the Riesz transform is not bounded in L infinity, because maybe you cannot symmetrize it by the whole L infinity, but maybe you can add something less such that the P plus will be bounded, however, but not, it's not possible. We will see a little bit later this. Okay, so H infinity is excluded by definition from this scheme. But, so what I mentioned, it is elementary, it is not. Okay, the last two, and this is very curious because, say, backward shifts, I already mentioned it today when I show you the colored table with the different corona in different, and it appears in Fourier multipliers here, this backward shift, and it appears here in U. I don't know whether it is coincidence or it is something hidden. So so I'd like to say that if A is symmetrizable, it is easy to see that the backward shift is defined and bounded on A. But this is the weaker condition. So let's consider an algebra where the backward shift is bounded. Then, given a polynomial in this algebra, and given a holomorphic function h without any condition, just in unit disk, we can consider this sum. This sum is not formal, it is well converged, because it is finite. Because S star to the degree of the polynomial is 0 and after. So it's finite sum, it is always polynomial. So for every holomorphic function, we have a linear map from polynomials to polynomials. And we will say that H is a backward shift multiplier if this mapping is bounded. Okay? And defines the multiplier norm as a norm of H S star. S H star is nothing but the anti-analytic Toeplitz operator over the algebra A. And this is the operator norm of this one. This is a Banach algebra norm embedded contractively in H infinity in view of the reproducing kernels in A. And the simple lemma says that A is symmetrizable if and only if A is embedded, A is a multiplier. So this is why H infinity is not symmetrizable, because H infinity is not embedded to the multiplier. For A equal H infinity, this norm, this space, is the space of Cauchy-Stiltiès multipliers. So Cauchy-Stiltiès, this is the functions of d mu of t minus z over t equal to 1. And this is a Banach space, and we can consider multipliers. This is exactly M of A. And the norm of M of A is stronger than the H infinity norm. There is no inclusion. H infinity is not included in multipliers of Cauchy-Stiltiès integrals. So, okay, so say for Berling-Sobolev algebra with the quite simple conditions that the weight is monotonic, we obtain immediately after a little computation that these multipliers are simply Wiener algebra. Okay? And for the Lipschitz algebra, the multipliers are H infinity. Why? Because the Lipschitz is the dual space to HP. Okay, HP is the Lipschitz alpha, where P is equal to 1 over 1 plus alpha, so less than 1. This is by the usual duality, and it is not locally convex, but it doesn't matter. What matters is that the norm of Lipschitz alpha can be defined by duality, and this gives immediately this equality, because the backward shift multiplier in the algebra is a simple multiplier in this space, and the just multiplier here is H infinity. So it is okay. Now the theorem. So we consider the holomorphic algebra symmetrizable holomorphic algebra A. So it is a holomorphic part of a symmetric algebra F, and such that there exists an auxiliary algebra G with the weaker norm. So we need to have with the weaker norm with the weaker norm between this holomorphic algebra and the multiplier. The multiplier norm is always weaker than this one because it is symmetrizable, and so F plus is embedded here. This is automatic. So here we need to choose G plus in such a way that the following embedding theorem holds. This is a very, very weak trace of Carlson embedding theorem. Okay, we will see that it's really the very weak form on this. Then we have this estimate for every n, for every Bezout equation in the unit disk. We have this estimate which depends only on the values of function on the unit circle, because f is in the circle. It is not on the disk. So we have the equation here, and we estimate it only by delta, which is defined on the unit circle, because this is symmetric. But in a compensation or in some so it is not so good that we have here delta square. Delta square is less than delta. Delta is less than 1. And so it's closer to 0. Okay. And we can estimate this k in terms of all constants which appear. I mean the embedding constant here, the embedding constant here, and this embedding here. So something. Okay? Now, so attention. It is the principal point of my talk, because I'd like to. No, I'm sorry. It's already just list of examples. But the principal point is to explain why it is elementary, why it is simple. And as usual, this a little bit technical part is in the end, when all think already to finish this talk. The sooner the better. So let me, however, give you some. No, but it's the drama of all talks, because you prepare the principal point at the end, but nobody has the forces to follow you. So okay. So let me consider, however, the examples. So for Berling-Sobolev, in particular Sobolev in the classical sense. So if p equal to 1, there is two cases, p equal to 1 and p greater than 1. P equal to 1 is called Berling algebra, and is much more elementary. So the necessary and sufficient condition that L1 is the convolution algebra is this one, of course. If we suppose that Wn is monotone, then we have G equal to Mf. The Wiener algebra, all constants are equal to 1, the projection equal to 1, and we obtain this inequality which was found by Omar El-Fallah and Mohamed Zarabi in 2005, published in London Mathematical Journal. But attention, there is some comment, because p equal to 1, unfortunately, so this is fortunately, if this algebra of really little bit smooth functions, okay, because why it's smooth? Because so you have that Wn is bigger than 1, so if it is grows even, so it's not bounded, so they grows to infinity, and we consider the functions whose Fourier coefficients summable with Wk. Yeah? So it's a little bit smooth. This function, then C1 is finite for every delta, and so our estimate has some meaning. Huh? This estimate, so this is finite for every delta, it gives something. Good or not, it is the second question. But however, it's not empty. But if Wn is bounded, and so we have the classical linear algebra with this, so it's just linear, so we are disappointed because C1, which is in the right-hand side, is equal to plus infinity for delta between 0 and 2.5, some surprise. But however, but here it is finite, however, huh? And so this inequality has some meaning, but not good. But this is the nature of things. I mean that this infinity, of course, it keeps not only for C1 but for Cn also, because Cn is grow monotonically with n, and so C2 is also infinity, C3 and so on. So it's you cannot improve it. For p bigger than 1, the situation is better in a sense. I mean that C1 of delta is always finite, this kind. And so we can compute all constant, and we can use our theorem. But unfortunately, for p bigger than 1, it's never Banach algebra. I mean that you never can change the weight to an equivalent weight for having this inequality. It is always wrong. So, but with some constant, it's okay. Which letter? K4. Okay. Okay. With some constant, it's okay. And unfortunately, this constant here, nothing to change, but it's entered in the argument. Okay. And so, if the function C1 grows fast when delta tends to 0, this grows K4 times faster. Okay. So, say for Sobolev power-like algebras, in particular for p equal to 2, we have this kind of estimate. So the power-like estimate, this one by the theorem, with some ABC calculated in terms of the exponent and the weight, and this one by some counterexamples. So A, B, C, D are different constants. So C is not equal to A, but what we can, I report you. Huh? Okay. For Lipschitz, so the multiplier norm which participate in the condition, as I said, this is just H infinity, the simplest one, and the corresponding inequality is more or less easy where it is. Let me here. The corresponding inequality with F Lipschitz alpha, and here H infinity is very easy to see that it works. But unfortunately, we cannot use it because H infinity is not symmetrizable. So we need to look for symmetrizable algebra, and this symmetrizable is just Lipschitz epsilon, where epsilon is small enough such that if n is between, if alpha is between n and n plus 1, so epsilon such that alpha plus epsilon is still in the same interval. And then, so we will give and just obtain this estimate. Such kind of estimates are known because Lipschitz is popular by many reasons, and the first theorem is proved even by Faizer-Shamayan in '85, but with different choice of the measuring of the norms of f, not this one, and of delta of the fj. So the both choices are different here and here, and so we can say that in my setting his result give only k which depends on n, and here k is just some numerical constant 20 or no, not 20. It's like this. But it is, however, more or less explicit in alpha. For alpha between 0 and 1, so what goes from the proof, it is just this one, which is not so good when alpha tends to 0 and infinity. And so I'm very sorry, but from what Anton Baranov said me, so I have a little bit more than 1 hour. So I counted for 1 hour 15. I'm sorry. So I mean that it's already passed, but not. So not announced, but true. Okay. So the proof is here. It is very simple. So it's very few slides. So first of all, the standard reduction. So we can consider holomorphic in the larger disk and use this weak completeness of the algebra that we can use the Mantel arguments to passing to the limit. Then we take the standard solution on the unit circle, which is not holomorphic in this way. And of course, the equation is satisfied, and this solution is real analytic on the disk. Then we follow the Uchiyama-Wolff proof of Carlson-Corona theorem, and observe that the d-bar derivative of this function, of this vector function, can be represented like as minus uf, where f is the holomorphic vector here, and where u is this matrix given by these partial derivatives. And so that if we can solve this equation with an antisymmetric matrix V, so with this condition, and we will set G equal to H plus V applied to the vector F, so we will get the equation. First, this is equal to 0, this is equal to 1, this is equal to 0 because of antisymmetry, and d bar, so oops, it is equal to 0, so it is a holomorphic vector which belongs to A, and we solve our problem. Now we will look for such a solution of this matrix valued d bar equation and estimate its norm. So we will use the standard Cauchy solution, which is given by Cauchy-Green integral here, which is very known. The important remark is that this solution is anti-holomorphic on the unit circle. Why? Because every elementary function which is integrated here is anti-holomorphic. Zeta is in the unit circle, and this is anti-holomorphic function. So the integral, depending on the parameter z, is also anti-holomorphic. And we don't need anything more. Why? Because P plus is bounded. Okay, so the arbitrary, this is a solution of this equation. It's very known, of course, and an elementary computation for the data which is a real holomorphic function, it is easy. And we don't need anything more, because an arbitrary solution differ from this solution by a holomorphic function, by a function whose d bar derivative is equal to 0. And but p plus is bounded in our algebra. So adding an analytic part, we can only increase the norm. Okay? So it doesn't matter. We will consider just this anti-analytic solution. And so G is holomorphic, so it's equal to P plus. So it's P plus H. H is a non-holomorphic solution, and P plus V of F. And we bound separately. This is absolutely trivial, nothing to do. We obtain what I showed already. This H is already estimated before. And the principal part is here, but it's also absolutely elementary, just by definition of the matrix here. Here is the principal point, absolutely trivial, but principal. I mean that V, J, K are coanalytic. Okay? So P plus VF is a coanalytic Toeplitz operator. And so the norm, so this is coanalytic Toeplitz operator, and so the norm of this is less than the norm of this coanalytic Toeplitz times the norm of Fk. And now the formula already mentioned by Al-Falazarabi, that what is Vjk explicitly. So we integrate in polar coordinate, and integrating by the circle of the radius r, we use the Poisson formula, and we obtain this trick. I mean UGK, which is here on the circle R, convolved with the Poisson kernel here, and P minus, which is because this is anti-analytic. And this one is not. The integral is co-analytic, but this one, of course, is not. And so we keep this P minus, and this is all. So we estimate by trivial trick, but using G, because G is the norm of G is stronger than the multiplier norm. So, but it is the good algebra. We also use this one. So G is the algebra with the stronger norm, and so this is this in the norm G, and we use yet another elementary computation, but UJK, which is the d bar which came from d bar of H, is in fact has this form here. And so, okay, so we can integrate. P minus we will eliminate. Here we estimate replacing G norm by F norm, which is larger than the algebra norm, and so on. So this does not depend on R. And here we integrate after integrating, because so which integrating this one, integral 0, 1. So I estimated what is inside of this integral, and so we get what we want. And I'd like to say that it is in fact several lines, and so this is my message, that in the corona proof theorem there is an obvious part which gives, however, something. Thank you very much.
Are there any questions or comments?
Are there any examples where the corona is small but not trivial?
Small, what does it mean? Huh?
Well, what does it mean? Well,
Yeah.
okay.
Yeah, I think that in Dawson example, it's however small. It is just, I think, it's not proved. I never see the Dawson paper, huh? So it's maybe written already, but I saw just a review in Mat Reviews. But I think that is just one analytic disk added in Dawson. So you have only one point, whereas there is a fiber, and I think that this fiber is just which come from this Fz, which tends to W what in my reasoning. I think this is the only parameter, and we can have only one, but maybe I'm wrong, huh? Maybe I'm wrong, because you know, because here, even here, not saying about different approaching, but even for the interval, so we have, however, some almost periodic behavior of the function. Okay, f of x, it is e to the I logarithm 1 minus x. So it is, and so I'd like to say that maybe there is something more than one disk. But on the other hand, the limit is always a complex number on the unit circle, and so I not think. I think it is. First, the second one in my last example with coronas, I mean Fourier multipliers on the unit circle L2 with some weight. There, however, they are identifiable, very simple. So I even write the visible and the whole spectrum. So in a sense, also the only one analytic disk is added. Huh? You know, this is what you see, and this is what you get. Huh? If I can say so. I don't know whether it means that you have a little corona or not. No, but you're right, because the most interesting thing, what I started, even if the question is not good formulated, what is the nature of coronas, of course? What happens? Why this invisible spectrum appears, and of what it consists? This is, of course, the most interesting thing. I don't know. I think that such kind quite weak reasoning can, however, orient you to something, to look in the literature, and I don't know.